All right, inverse functions. So yesterday we kind of reviewed these through this handout, and I want to make sure we understand. A horizontal line test tells us if a function is one-to-one. In order for a function to have an inverse, a function must be one-to-one. So this is the very first thing you have to think about when you think of a graph of a function. So the first function I think about that fails a horizontal line test is a parabola. Because if you think about y equals x squared, it's definitely going to fail a horizontal line test. So an x squared function doesn't have an inverse. The reason it doesn't have an inverse is because it doesn't have a one-to-one and only one-to-one both direction point. What we do in order to make an x squared have an inverse is to limit its domain. So that's a big part of what we're going to do in here is limit the domains to find inverses. So then we talked about f of x equals x cubed. X cubed will have an inverse. It will have an inverse because it's this red graph here. So the red graph passes the horizontal, it passes the vertical. It's odd, it's symmetric about the origin, and it's one-to-one. So odd functions that are unmanipulated are one-to-one and have inverses. We just talked about x squared, so x squared is even. It's symmetric with the x-axis and therefore not one-to-one. In order to determine if a function is one-to-one, we switch the x and y values, and then we solve for y. So this is the little part that I don't think we focused so much last year on finding inverses, which is making sure we define the new domain and ranges and verify that function composition is the identity. So fog equals x and goth equals x tells me that two functions are inverses. So if you're given an f and you're given a g, we know they're inverses if we plug one into the other. And when we plug them in, we need to get back out x. So if you plug g into f, you should get x. If you plug f into g, you should get x. If you get anything other than x, then they are not inverses. Okay, so here we have f of x equals 2x squared minus 1, and g of x equals the square root of x plus 1 all over 2. It's important to note that for this one, in order for these to be inverses, you have to say that x is greater than or equal to 0. So when you graphed it, you probably had the entire parabolic curve. So in order to see the inverses, we have to almost get rid of the second half of that curve. The reason for that is because the domain of g has to be greater than or equal to 0. Therefore, the domain of g is such that x is greater than or equal to -1. And if you look at that purple graph, that purple graph's range is the domain of g. So the range of f, which is purple, is the domain of g. So the range of f is the domain of g. Inverses are symmetric about the line y equals x. So if you look right here and you would draw a line through y equals x. You draw a line through y equals x. These graphs are symmetric. Does everything make sense so far? Okay. To find an inverse, which I know we did last year, what you're going to do is take the x and the y's and flip them. So this would become y equals x cubed instead of the f of x. Once you have it in terms of x and y, you flip them. So you get x equals y cubed plus 2. Subtract your 2 to both sides. You get x minus 2 equals y cubed. To get rid of something cubed, you cube root it. So we get y equals the cube root of x minus 2. And then if you go back to function notation, it's f inverse x equals the cube root of x minus 2. Same thing here. How are we sure a function is an inverse? That's when you do function composition. So you take the inverse function you got, plug it back into the original. So the inverse is the cube root of x minus 2. We're going to cube it, add 2. So the cube root of something cubed is just what's underneath. So you get x minus 2 plus 2. The negative 2 and 2 cancel, and you get x. So that's doing fog. Goff would be the reverse. So it'd be f inverse of f of x equals the cube root of x cubed plus 2 minus 2. So the plus 2 minus 2 cancel. You get the cube root of x cubed, which is x. And then do you have this one down at the bottom? Just without the graph. Okay. So, what is the slope of a line y equals 4x plus 1? 4. Graph the line and its inverse. So we can graph its inverse easily if we had a graph because we know that whatever points are on the blue, which is the original, the inverse dots would be the reciprocals. So if you have the point 0, 1, then on its inverse you'd have 1, 0. If you have the point 2, 5, then on its inverse you would have 5, 2. So if 2, 9 is on the original, what point does it correspond to on its inverse? A flipping of it, which would be 9, 2. So that's this point right here. The slope of the line at 2, 9 on the original function is the reciprocal of the slope of the inverse. The difference is that the slope of the inverse is calculated using the point 9, 2 instead of 2, 9. The slope of the inverse in this case is 1, 4. And then that picks up with where we started earlier today, walking through the idea of an inverse and its derivative. So we have, there's kind of going to be 2 or 3 methods that we call them. And when you do your homework, I gave you 5 of method 1 and 5 of method 2 because I want you to see both methods because the idea is that they're worded differently and they're going to give you different example wordings. And that's going to change how you want to do a problem. So method 2 can be used when finding the inverse of a function that is messy. So you find the inverse of the function by interchanging x and y. Don't worry about solving for y. We're going to use implicit. So sometimes if you're given that x value and you can't find the y, like let's say, like you know how we did the p, q, and we flipped them? Sometimes the flipping isn't going to be easy. So what we do is we actually take the derivative of the inverse. So we will flip-flop all the x and y's and take the derivative of the inverse. But we're not going to actually solve. So in the homework, I was like, okay, find the inverse function, and you had y equals x cubed plus 2, flipped your x and y's, and you found the inverse. This time, instead of actually finding the inverse, you're going to flip all the x and y's, and then you're going to take the derivative using implicit. So, let's try. I think I'm more confusing speaking. So the original is y equals x cubed minus 4x squared plus 7x minus 1. The rule for finding the inverse is to flip the x and y's. So this would become x equals y cubed minus 4y squared plus 7y minus 1. We cannot solve that for y. It's impossible. But in Calc, we have a method where we can use implicit. So we're going to derive it and actually find the derivative of the inverse. So when we take the derivative of this, it will represent the derivative of the inverse. So the derivative of x is 1 dx dx. The derivative, and hey guys, after our quiz yesterday, we don't have to write dx dx anymore if you don't want to. So it's 1 dx dx equals 3y squared dy dx minus 4 times 2y dy dx plus 7 dy dx minus 0. 4 times 2 is 8. You totally could have multiplied them. I just wrote 4 before I did. So what we're going to do is get anything that doesn't have a dy dx on this side, which is nothing, and then we're going to GCF out the dy dx. Okay, and that's on your side. So then you get dy dx equals 1 over 3y squared minus 8y plus 7. Doesn't this kind of look like what we did before? 1 over the derivative? Except for now it's not 1 over the derivative of the original, because that would have been 1 over 3x squared minus da-da-da. It's 1 over the inverse. So the question says f of x equals x cubed minus 4x squared plus 7x minus 1 at x equals 1. So what do I need to be able to plug into this? I need the, what letters are these? Y. So I need to plug 1 in to get y. So you get 1 minus 4 plus 7 minus 1, which is good. So what that means is we're going to find the derivative, or dy dx, at 3 . So what that means is the derivative of f inverse at 1 is 3. So again, that's like saying f inverse at 1 its derivative is 110. So the derivative of f inverse at 1 is 110. And that's at 1, not 3, because of the way the points work. So example 4, if f of x equals x squared and we're given the limited domain of x greater than or equal to 0, it makes it 1 to 1. Find the derivative of f inverse x at x equals 4. So again, our goal is to find the derivative of f inverse at 4. That's what we're ultimately looking for. The derivative of f inverse at 4. So if we do this using method 2, the rule of thumb would be to flip-flop your x and y's. So f inverse of x would really equal or become x equals y squared. Taking our derivative of x is 1. Derivative of y squared is 2y dy dx. So dy dx equals 1 over 2y. So f inverse at 4 is really like finding dy dx when y equals what? Well, we'd have to plug 4 in. 4 squared is, so this is really like when y equals 16. You can compare this to method 1. Right, so method 1 is what we did earlier. So method 1 said, okay, find the derivative. So that would have been like saying y prime equals 2x. If you wanted to find f inverse of 4 for that, then you had to know what the y value was of the 4. So you flip-flopped it again. And that would have put your 16 here, and it would have been 1 over the 2 times 16. So it works out just the same. Does that make sense? So it's possible really to streamline both of these all into one. So it says that f is a function that is differentiable on an interval. If f has an inverse function, then f inverse is differentiable at any x from the original, as long as it does not equal 0. So f inverse prime of x. So this is another way of writing f inverse with like the prime symbol instead of writing the ddx out in front. You write the f inverse in parentheses, put the prime between it and the x. And it's like saying 1 over the derivative of the inverse. So this method will always kind of end you up with a y. So just a streamline to that one. So what we could do, so again, it's f inverse prime of x. So what we'll do is essentially the x now is 3. It's going to equal 1 over the derivative of the inverse. So the inverse of that would be the flipping of the x and y's. So you take your derivative. 3 times 1/4 is 3/4 y squared. We don't have to write our dy dx's if we're using this formula, which is super goofy. We need to know what the y value, though, is when x is 3. So you get 27/4. Well, 3 minus 1 is 2, so you got to get a common denominator. So you get 8/4. So 27 plus 8 is 35/4. On a non-calculator AP question, you can finish it like that. On a non-calculator AP question, you may leave it like that. That is considered a numerical answer. So if you have something like 35 squared, which we do not know, you may quit at that. Only for like big questions with big numbers. So, yeah, gross. Okay. They love tables and charts. They love tables and charts. So, we have g of x, we have g prime, and we'll say that f and g are related. Find g inverse prime of 1. So to find g inverse prime of 1, we'll use that same idea that we just had. So here's goal 1. So you have to find f inverse or g inverse of 1. So that's like saying, okay, what is g of 1? It is 0. So the inverse of that would be the reflected point, right? So if you have g of 1 equals 0, g inverse of 0 would equal 1. So kind of see like that connection. So G inverse prime of 1 would be like saying, okay, what's G inverse of 1? Well, that's when, so if this goes 1 to 0, the inverse goes 0 to 1, the inverse would go 1 to -1 from a table. So I just like kind of picked this as like a random to like give you the idea. So like original goes 1, 0, inverse goes 0, 1. So if you're given the inverse as 1, so you go to the table, it gets negative. So G inverse prime of 1 is like 1 over G prime of -1. G prime of -1 is that. Do it again. So G inverse of -3 so you go to this line is 4. So the derivative of G inverse of -3 is 1 over G prime of 4. Okay with that? I know that like it's like a little tricky to see, but like once you do it, it's like, oh, that makes sense.